Humans are visual creatures. The brain uses more information from the eyes than from any of the other body senses. Light provides us with the most detailed information about the world around us: shape, size, and color. It's also the best way we receive information from a distance, beyond the sense of touch, farther than smell or sound. It can even reach across a galaxy. When we looked at the electromagnetic spectrum in our last unit, we saw that visible light occupies a very small section near the middle. We also saw that light can be described as a moving electromagnetic disturbance, an electric and magnetic field traveling together as an electromagnetic wave. Changing the frequency or the wavelength of the wave changes the color of the light. Lower frequency, longer wavelengths produce red light, while the higher frequency, shorter wavelengths produce blue light. But light has a peculiar nature. It seems to have a Jekyll and Hyde or double identity. Depending on the condition, light behaves like a wave. But light also behaves as though it's a stream of incredibly small particles, something like a line of very tiny billiard balls. In the same way billiard balls bounce off smooth surfaces and change their direction, a stream of light particles does the same thing, bouncing off mirrors and smooth surfaces. On the other hand, light as a wave will display the same type of interference pattern we've already seen with water waves. When light waves interact, the same type of construction and destruction shows up. Overlapping two beams of light produces interference, and it shows up as patterns of light and dark bands. This effect can be assembled into the eerie images of a hologram. A most peculiar effect of a hologram is that when you cut it into pieces, each piece can still give you the entire image. This dual nature of light needs to be understood in order to design and use the tools of optical technology. In this unit, we'll look at these two different natures of light separately. First, we'll look at ray optics, the study of the particle nature of light. Light travels from one point to another as a well-defined ray, hence the name ray optics. We'll see how the shape of a lens or a mirror affects the path of a ray. And we'll see how light bends when it passes from one medium to another, such as from air to water, or from water to air. Light rays can be used as handy tools that enable the technician to predict where the light will go. Knowing how to guide the light with mirrors and lenses means that it can be put to good use, such as in the optical system of a telescope. In the study of wave optics, we will learn that as a waveform, light does not always travel in straight lines, especially when passing through very small openings. Like water waves that spread out on the other side of two openings, then create an interference pattern, light does the same thing when passing through narrow slits. After we learn about ray optics and wave optics, we'll look at a very specialized form of light that has countless practical uses, the laser beam. Its utility is based on three important characteristics. First, it consists of only one color, or one frequency. Second, all the elements of the beam stay together over very long distances, such as across a field, without the use of focusing lenses. Third, all the elements of the beam are parallel and in phase with each other, so there's no interference between them. That's one of the reasons the beam does not spread out like a searchlight beam and can be used as a very accurate reference beam, in this case to make a field perfectly level. Laser beams can be powerful enough to cut steel and precise enough to read coded information, like the universal product code used in the supermarket. Finally, we'll look at optical systems, where all these principles are put together to make up our modern optical technology. The human optical system, the eye, can be repaired with the surgical precision of a laser. Eyes can be improved with artificial lenses. The lenses enable the eye to see better, to see farther, or to see in more detail. Anyone who works with an optical system needs to know the effect that different materials have on light. And in the television business, this is used quite a bit. For example, if you want to change the light that's going into this camera right now, one way is to use a filter. This particular filter is called a diffraction grating. We'll be seeing these in one of our subunits. But what it has is a prismatic effect. It breaks light up into colors. And if I simply hold it up to the lens here, you can see that it causes this lovely star effect. Sometimes you use that during rock concerts if you want to highlight somebody, because it breaks the light up into its individual colors. So simply by putting a filter in front, we've changed the character of the light going into the camera. The lens that's on the camera itself is also affecting light. The shape of that lens is taking the light that's surrounding me right now and guiding it in. But that particular lens is fairly narrow. It can only see a space about from here to here and here to here. I have here a wide-angle lens, and it's a different kind, it's a different shape, and what it does is accept light from a much wider angle. It can take light all the way from over this way and over this way, guide it down, and give you a clear image into the camera. But the image you get is very different. And I'll show you what I mean here. I'm just going to put this one on. We'll take one lens off. All right, now this goes to white because there's unprocessed light here. And then when we put the wide-angle lens on, you'll see a very different image. Okay, now here's the wide-angle lens, and we should see quite a difference. Now, I haven't moved, the camera hasn't moved. All that's happened is that we put a different shaped lens on, and now it's accepting a field this wide. This is the kind of lens you'd use in sporting events when you want to see a squash game or a football game, and you need to see a wide field. Unfortunately, it's so wide that it actually distorts a little bit. If you notice over here, you can see the ceiling isn't straight anymore on this lens because it's so wide it actually distorts it. But then, if you're doing special effects, say you're doing an Alfred Hitchcock movie, you can do weird effects by distorting the human body. Well, seriously, one of the most interesting applications of optical systems is providing eyes for machines that have already got brains, arms, and fingers. The next generation of robot will have machine eyes that will guide their machine hands. Robot vision systems will enable the manipulation of parts without the intervention of the human visual system at all.
Warning, insufficient illumination to perform functions. Warning, warning.